is here is to enter into the stochastic part as smooth as possible. But you know, there is a point where we need to touch the stochastic part anyway. Now, let me spend a word. So, you know, our goal would be to estimate a set of parameters. So let's see what I really mean about that. So, you know, in general, the kind of problem that you are asked to solve is the following. So we have some data, which is X. We have some modeling of the data. Okay, the data depends on the index I. Don't look at the others. Look at these as simple. Okay. So now this data depends on the index I. This index can be time, can be anything. Okay. Now, since in the course I removed the two-dimensional part, so there is only one variable. Last year I was doing bidimensional signals, so which is like images or movie. Okay, a movie is a three-dimensional is a set of pictures. Okay, so it's a set of matrices. So, but you know, skip about it. So, you know, I have a certain sample. Now this sample can be represented, we say model. So this sample is represented by a function depending on the set of parameters theta. Then plus some impairment, some noise, something that, you know, is not expected in the data. Now X time is called data. Okay, X is time. X is called measurement. S is called observation. Okay, so it's what you get. So our goal is the following. We have an X of I, and we have a set of these X of I. So we make a set of measurements. And this measurement depends on the parameter theta. Now this set of parameters, as I said, is a set. So this is a set of parameters, so thick. So this is a set of parameters, theta is a vector. So this one, you know, is in a very generic way, is a theta 1 to theta p. So, you know, is a vector of parameters. Now, vector is just a way to say is the ensemble of parameters. So it depends on the set of parameters. Okay? So if rather than that, you know, I can write that xi is equal to s. Okay, that depends on I can be the time, just to figure out, so you know, I can be the time. And then, you know, the sampling time, this is time as well. Okay, so the sampling time, then, you know, depends on the set of parameters. So this is a set of parameters, is a set of numbers, theta 1 to theta p. Okay, and then, I mean, since it depends on that, but you know, because of this dependency, sometimes, you know, there is a component that, you know, it doesn't match with the data. And this component is called noise. This is W. Okay? So you remember the discussion we did with the subspace and subspace, you know, projection and everything. So every time I have a measurement, since my data has to stay in this plane, then you know what I can justify with my, you know, my set of parameters is only that part which is the projection of the data onto this plane. Now, when I project the data onto this plane is what I do, commonly called filter. So when I filter, I take the data and I project. So I look at the data, interpret the data with my alphabet. And my alphabet is something that moves in this plane. So the component, the orthogonal component is noise. Okay? Now, sometimes, you know, we are not always so lucky because sometimes the noise does not simply contribute to a deviation of the vertical part, but it might have a part that is moving, you know, in the vertical and then a little bit on the diagonal way. Now, if it is, you know, if this vector is not perpendicular, but is a little bit tilted, so we have this component that, you know, it doesn't care because I can filter out. But this component that deviates with respect to the plane is something that I cannot separate. So, you know, in any case, that component is affecting my estimate of theta. So my goal is to get data from a set of measurement x. And this is our goal. So starting from now till the end of the semester, we will work with this problem, which is estimating a set of parameters. And this set of parameters is describing all the phenomena that I am observing. Now what I'm doing today is just to touch very simple set of problems that we can imagine we have a set of parameters to estimate. So I have a set of problems, very easy problems, but it seems a toy problem, but they're not toy problem, they're practical problem. Okay. Now we have seen that. By the way, theta. Let me give you one additional hint. Okay, we will continue on that, but just to put something on there. Now the theta that I'm considering, this theta, okay, is what I'm looking at. So I put as a question mark, which means my unknown is that theta. Okay. Now this set of theta might be deterministic or random. Okay. Now let's make a very simple example of that. What is a deterministic? Deterministic means non-random. Okay. So if you like, rather than deterministic, you can say it's not random. Okay. So if my set of parameters are not random, means it's a number. I don't know. Where is this phone? It's there. Is it random? No, it's a number. Is, I don't know, this coordinate, that coordinate. So it's three numbers which describe the position of that phone. This object in space is deterministic because it stays there, right? So the object is there. Now the goal is that you want to estimate that object. Okay? So that the position of the object is deterministic, absolutely deterministic. So it's not random. Now let's make the problem slightly different. Suppose that now I put a tent in front, okay? And then I move the object. Now if I ask you where is the object, then start saying time. Because the time matters. Because the fluctuation of the object itself matters. So it depends, how the object is fluctuating. Now, there is a way how the object fluctuating, and the way of the fluctuation, the way the object is fluctuating is represented by a random variable. So it's better to consider the position, in this case, as a random variable, because it has some uncertainty, it fluctuates, and perhaps if you have a tent, sometimes you don't see it. So imagine I put a tent, then I put a tent, you see, put a tent, you see it's moving. Now, in the meantime, between the tent is down and the tent is up, you don't see it. Okay, so it might go everywhere. Now, in this way, I represent my set of parameters as random. We will see that the way to treat the problem in this case is totally different from the way to treat the problem in the other way. So you get practice on how to treat the problem in a deterministic fashion and how to treat the problem in random fashion. Okay? Now, so you see, this one is random. And by the way, the noise, W is the noise. The noise, the best way to represent the noise. This is noise, impairment, blah, blah. So everything that cannot be described. So usually this noise is described by a random variable. Okay? So for this reason, since we want to be completely sure that we have a perfect control of the problem, then for this reason we need to study the random aspect of the problem itself. Okay? Now, right now is not the focus today, but I'm preparing you for the next weeks. Okay, the next week we need to be prepared to represent, to analyze problem like this one, where the noise is random, and sometimes the parameters are random. Now, when I have a set of, when I have a set of measurement, okay, and assume that now I have a set of measurement, which is a set of observation, the data. My data set is composed by n samples. So my vector, before saying a vector. So what I do is, rather than representing as a set the data, okay, this is a set of samples ordered with I equal 1, 2, blah, blah, n. Okay? Rather than say my data is a set of samples, I prefer to stack, to put all the data into a vector. And so if I put everything into a vector, my new representation, which is a way to represent the data, is that my n samples, okay, are ordered into order, just ordered into a vector because it's convenient. And then, this means that the model is still the length n, and W, which is noise, has a length n. So in a very compact way, I can say that the data x, which is a vector, is equal to s theta, which is, it depends on the parameter theta, plus W. W is a vector of n samples of noise. So this is a compact way, okay? Here is n, here is n, here is n. Okay? Which is the same representation, but it's much more compact.
So you have n minus 1 W.
Mistake. Thanks. Okay. Then this is the set of data. Okay. No. Simple, right? Now let's specialize in some setting. Now, I can make a problem where the model is linear. So remember, before it was x equal s vector depending on theta parameter plus w, okay? And this one was a vector n times 1. This is n times 1. This set of parameters is p times 1. And this is w is n times 1. Okay? Rather than describing the problem, if we are lucky, okay, we get the linear model, which is, a linear model means that this s theta is linear. Okay, actually it was here. So that means it's linear, if we are lucky. Then my age is describing the problem. Now we remember that this means that since I have n times 1 and this matrix is n times p, which is described here, and h is p times 1, so suppose, which is mostly the case, not always, but mostly, suppose that n is much, much larger, or at least larger or equal than p. Okay. That means that the vector x, okay, is a point in the n-dimensional space, n, capital N. And this point is obtained by putting together vectors. And what are these vectors? The column of matrix H. So recalling what we were discussing last time, matrix H contains a set of vectors in column. Okay? And then these vectors, okay, and these vectors, so vector 1, vector 2, blah blah blah, these vectors, set of vectors are describing the problem itself. Okay? So we remember the properties. Now let me make just a refresh of what we have been doing so far. So I have a new page. what we know about this kind of problem? Okay. What do we know about this kind of problem? So remember, the problem is x equal h theta plus w. W is describing everything that I cannot say it's a signal. Okay, so it's something that is affecting usually, normally, my measurement. Now we solved this kind of problem. So if I want to get the data, so how to get data? Now, to get data, what I do is I can write a least square problem. The least square is the following. So usually the least square problem says, okay, x actually is equal to h times theta, but it's not really exactly that because it's approximately, because there is some impairment. So what I do is I write the error. And the error is x minus h times theta. This is what we know. So what I'm saying here is everything that we are supposed to know. Now I'm simply refreshing your memory, okay? So this is the error. And by the way, the error is n times 1. Okay? So if I want to get the theta, in order to get theta, what I need to solve? I need to solve, a least square problem. The least square problem is the following. I want to minimize, with respect to theta, what? The epsilon transpose epsilon. Okay. Now, this means that, so I need to, this epsilon transpose epsilon, actually, let me better focus. This one depends on theta. So epsilon transpose depends on theta. Epsilon depends on theta. Okay? So, what we did, we wrote it. So we wrote this phi of theta. Because this is a function, it's a scalar. And this phi of theta is equal, now I keep it short so you can see pages on that. So it is theta transpose, then it is h transpose h, then it is theta minus 2 times, x transpose h theta, then you write this way, plus x transpose x. Okay, this is the phi function. When I just aggregate the pieces and so on. So, in order to find the minimum, what I need to do, okay, after that, I need to take this one, compute the gradient, set to 0, which is computing the gradient with respect to 0 of theta. Okay, and so on. And so, when I do this, okay, I get that theta hat least square. Now I put the least square on the bottom, which means it's a solution that I get with the least square method is equal to it's h emission. It's real h transpose h to the minus 1 h transpose x. Okay. So it's just an operation that I get, that I do. By the way, sometimes this one is called pseudo inverse, okay, because it's not an inverse. Huh? And so sometimes I write that it's a pseudo inverse of x. Okay, that in MATLAB it has one line of instruction. Now, this is what we know. Okay, so everything I've been writing now is something that you have in some pages. Okay. So what we did in the first week. Now let me make a step forward. So let me plug in here. So x, what is x? X is h theta plus w. But now this theta is the true one. Let me call theta 0. Okay? Theta 0 is the true one. So when I plug in there, okay, so in red is when I plug in. So it means, everything I use kind of color coding as far as I can. So I have h transpose h to the minus 1. Then I have h transpose h theta 0 plus h transpose h to the minus 1 h transpose w. Okay? So this one is the identity. So continuing, this one is theta 0 plus h transpose h to the minus 1 h transpose w. So what can I say? I can say the following, that this way, the least square solution is equal to the true one, because it's theta 0. This is the true one that I was looking for. Plus the h, which is a perturbing w. So any perturbation on w, which is the noise, is deviating the solution of theta, because it's a perturbation of w that enters into the value of theta that you get. So this deviation depends on the noise and w, and it depends on the noise w and h. So depending on how you design h and how is, because you cannot design w, how is w, then you can match, so you can make this number minimum, smaller. Okay? Pretty clear? Good. So now we have seen that the linear problem is very nice because I can immediately get a solution. I have no control. Right now, you have no control. Right now you are too young to know how to control that. So there is this phenomena where you have a poor control, let me say. You have poor or no control at all. Because you have a noise, okay, and then you have age. And so, we will see how to make this term to be minimum. But right now, we have no control. Now, let's see linear problem. So is it clear now? So every time you have a linear problem, you know how to solve it. So every time, every linear problem that I'm going to discuss now, you have the way to solve it. And by the way, it's even more. You have a way to solve it, and you have a way to understand what is the phenomena, what is the impact of the noise onto the solution theta. So how, theta has been perturbed by this term. Okay? Now, let's start. Let's consider, a very simple problem that, let me say, more or less we have been touching. Okay? This is a linear regressor. So, when I was talking about how to get rich, okay, by regressing the stocks data at that time, I just introduced that as an example. Now let's make a little bit more rigorous. So let's assume that our model is linear. So what is linear? Linear means that I have a set of points, and my goal, okay, is to find the line which is fitting our data. Okay. So this line is given by two parameters. This is A, and the slope is called B. Okay? So these measurements is indicated as T1, blah, 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 and then the generic one is Tn. And then the data here, which is the measurement, is Xtn. Okay, which is a true data. Now, so let's write the linear model for that. Because once we know how to write a linear model, then we can solve it. And then we can find A and B. Remember, my unknown is, is A and B. So I have the points, I need to get A and B. Now, before getting, I need to write the problem in a formal way. Now, the way to write in a formal way is the following. Assume that I have a set of samples, so I have xtn. I model these samples as if are given by A plus btn plus some noise. Now, but I'm not happy with this. I want to write everything in a matrix form, because if I write in the matrix form, I know how to solve it. Okay? Because remember, my solution is this. So what I want always to find if it is linear, if the model is linear, okay, which means x equal h theta plus w. My least square solution is h transpose h to the -1, and then h transpose, and then with data. Okay? Remember, what I'm using is that one. So every time I try to write in that way, because once I write in the first way, I know the solution. Okay? So, as you imagine, this is the easiest way. Okay? So in order to write in that way, so what I do, I simply put the samples, the n samples on the column. So I put all the samples in column. Okay? So these samples of column, is just samples of n measurement. This is the data. Okay? Then I can write my linear formula, which is a linear, linear regressor. Okay? I can write by putting a vector of 1 and a vector of time values. So this matrix, which is, is organized in this way. I have a vector of 1 and a vector of time samples. Okay? So this matrix, okay, is describing perfectly my data, because I have 1 multiplied by A, which is A plus T1 multiplied by B. Second, 1 multiplied by A plus T2 multiplied by B, and so forth. Okay? So convince yourself. Plus W. So this vector, sometimes I call the vector 1. When I indicate as 1, means it's a vector of all 1. 1, 1, 1, 1, 1. Okay? And this one is a vector of the time. So this matrix here, okay, is a matrix that has n times 2 samples. This one, okay, these are theta, our unknown, which is, in this case, the unknown is intercept and slope. And this one is W, the vector of, okay? Here. Huh? Now, as an exercise, before moving forward, you can rewrite this problem this way. Let me do it. Okay. So if I rewrite the problem, which is x equal, now it is vector of 1 and vector of time multiplied by theta plus W. So that problem can be rewritten this way. Okay? Now, since I want you to get practice, okay, so let's implement the second part of the solution. Right? The second part. Let's follow. Okay. So since this one is h, so I read there, so I say x hat least square, which is essentially a hat b and so it's an estimate of A and B, okay? That one is, okay, is H transpose H. So what is H transpose? H transpose means that I take this one and make a transpose, okay? So let's make on the side. So H transpose means that I have a vector of 1 and the vector of time, and then I need to make a transpose. So what does it mean? It means that, you know, I have two vectors, but since when I make a transpose, I flip it and make 2 rows, okay? So this is equal to 1 transpose and T transpose. Okay? So I write it here. So I have 1 transpose T transpose multiplied by 1 T. Everything to the minus 1. Okay? So this one is H transpose, and that is H. Okay? You see there? Fine. Then what I need is, you know, I have one part that is missing. Let me move this one here, okay? So I have one part that is missing, which is H transpose, but you know, we know what is H transpose. H transpose is 1 transpose all the time organized in vector transpose. Everything multiplied by what? By x. Okay? And this one is H transpose. Now, this problem can be solved in a block partition matrix. What is a block partition matrix? It's a matrix where the entry are matrices. So we are introducing now, you know, a new form of matrices that are block partition matrices. So let me make just a digression. So this is, you know, okay. The second one is the following. What is a block partition matrix? You know, if I have a matrix A, consider H. If I have H, which is divided into H11, H12, H21, and H22. Okay? And these are itself a matrices. So if this H is a matrix, so this one is a matrix, okay, which is H, of matrices, which is H11, H12, blah, blah. Okay? When I have a problem like this, okay, this matrix H is called block partition matrix. Now the beauty of this block partition matrix is that every time you need to make a multiplication among a block partition matrix, they work with the multiplication as if they are scalars, which is very, very powerful. So if I do this way, okay, this becomes, let me make it, okay. Okay, so this becomes, you know, so I have a 1 transpose 1. So this multiplied by that. So this multiplied by that. This multiplied by that makes 1 transpose 1. But this is a scalar, is a number. Okay. Then at second position, I have a 1 transpose T, using the same principle. Third position, okay, is T transpose 1. And fourth position is T transpose T. So this one now is a 2 by 2 matrices, is minus 1. So it's the inverse of the 2 by 2 matrices. Multiply by what? Now, you know, multiply by. Now, I apply the same trick. So I have 1 transpose x. Okay? Now, 1 transpose x, you know, is a sum of x. So it's x1 plus x2 plus x3 plus x4, blah, blah, blah. Okay? So let me write, you know, this way. 1 transpose x. And then the second one is t transpose x. Okay? Which is t1 multiplied by the corresponding value. T2 multiplied by the corresponding value. T3 multiplied by the corresponding value, and so on. Okay? So this one is t transpose x. Now, what is 1 transpose 1? I mean, let me show you here. What is 1 transpose 1?
Number of samples. Number of samples.
Is n. Okay. What is 1 transpose t? It is t1 plus t2 plus t3 plus t4. So it's a sum of tn and going from 1 to capital N. Okay. So what is now, you know, t transpose 1 is the same. Okay. And then what is t transpose t?
Summation of the squares.
Sum of the square. Tn squared. N equal 1 capital N. Okay? So I have a matrix 2 by 2 where I have n. Here is the sum of Tn. Here is the sum of Tn. Here is the sum of Tn squared. You see? This one does not depend on the experiment. So I can compute once and that's it. Okay? So every time I collect the n samples, I have the same matrix. I invert once, forever. I don't need to revert all the time. Okay? Now, you know, we will see this concept again later, but you know, it's important that it goes into my mind, to your mind now. Because I mean, my philosophy is that I repeat everything. I mean, if I need to say this course will be zipped in 2 weeks, 3 weeks at most, okay? So the other part is say, what am I going to do the rest of the semester? I repeat the same concept many times, okay? So this is now the second time I repeated the story of least square, okay? You will see the least square repeated at least 3-4 times more, okay? Anyway, so let's move forward. Now, if, you know, if the samples, if these samples, T1, T2, T3, T4, are regularly spaced, now what's happened when they are regularly spaced? This is time. What's happened, you know, if T is regularly spaced? Now that means that the time is regular, okay? T1 is 1, 2, 3, 4, 5, okay? So usually what I do is just I relabel the samples, and then, you know, these samples are, you know, if are regularly spaced, then, you know, it's, I count by position. That's it. So I have a T1, T0, T1, okay, T2, T3, but, you know, since they are regular, so if they are regular, you know, it's enough that I get this delta T, and then, you know, I say the first sample, spacing delta T, the second sample, spacing delta T, and so on. Okay? But, you know, the concept is the same. More. Rather than make, you know, the linear regression, I can make a more esoteric regression, like a polynomial. Arbitrary value of the polynomial, right? Now the polynomial, the model in polynomial, okay, the model, you know, it depends on a set of parameters. The parameters, even if it's polynomial, since the coefficient of the polynomial are my unknown, the model is still linear. Okay, it's still linear. Now let's see 1 case. Okay, I have a nice picture. Okay, which is the same picture you have in your note and in the book. Okay, so suppose I have this set of samples. Okay, and my goal is that I'm sitting here, which is Tn, and I want to predict Tn plus 1. Okay, we have seen by Apple stocks or by stocks, any company. So, and then I want to predict, and this is my error, delta x. Now, if I make if I have these set of samples, and I make a linear regression, then my line is going to be like this. And so it's clear that if I make a linear regression on that, my estimate, my predicted value is this one. So this is the predicted value for linear regression. Okay, the linear regression, which is a plus b times Tn. Okay, but it's clearly wrong. I mean, I would never invest. I would never make this as prediction to decide if to sell or to buy. Right? Okay. Because remember, the way if you want to get rich, you need to sell when it's. You need to buy when it's going up. You need to sell when it's going down. Okay. So when you predict that it's going down, then you are selling. When you predict that it's going up, then you keep it. Okay, and you will sell tomorrow. Okay, and this is the trick. Okay. And given the data that I gave you, what I'm saying here, you can apply to the data. And then you can make a simulation, assume that you invest $1,000 at the beginning, okay, of the period that I give you. So you can say, I invest $1,000, and then I want to see how much I can gain. And then you can simulate a different setting, different strategy. A very conservative strategy. I put $1,000, it's growing, okay? And then you get, at the end of these 4 years' time, you get approximately 3 times, okay? So you gain 3 times, then you are happy. But if you make a trick that you sell and buy, so you sell when everything is going down, and you buy when it's going up, and then if you make this trick, then probably the money that you get is not 3 times, but probably you gain 4 times or even more. Okay? So then, you can simulate. So, I would go back, if I were you, I would go back on the data that I gave you, and I gave you those data specifically to practice you. So you can practice. And then you can practice without risk how much gain you make if buying the stocks of that company. And then you can download more companies, then then to do it. Okay? Perhaps some of you, I am pretty sure that some of you, when graduated, will work in finance. There are many of those that work in finance at the end of the graduation. Okay? So perhaps if you start doing this trick during this semester, perhaps we work together, we look at together, okay? And we see and we tune the algorithm. This might work. Now, let me go back. So that means that, my regressor is not linear, it has to enrich a little bit. And so I can make a quadratic. So if I make, for instance, if I make a quadratic regressor, probably, the quadratic regressor is going like that. Okay? So this is a quadratic one. Quadratic means, this is a plus b tn plus c tn squared. Okay? Remember, a, b, c are the unknown. Then, I don't know, I can make a 4th order polynomial. And then, it's going this way. And then this one is a p plus b tn plus c tn squared plus d tn cubic. Okay? Now, rather than calling a, b, c, and d, okay, I call theta 1, theta 2, theta 3, blah, blah. So I can exploit the p-order polynomial. So let me see. So this is the way I can regress the data. Okay? So I can regress the data with theta 1, theta 2, tn, theta 3, tn squared, blah, 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 up to theta p, t to the power p minus 1. Okay? So this one is the power p minus 1 polynomial. Then I'm doing exactly the same as I did. So I will write everything, you know, in a matrix form. So we write everything as x equal is linear because I collect this is the age, and then I put it here, theta 1, theta 2, theta p minus 1. Okay? Sorry, it's p. Then you know this is a vector with a p parameter. Then plus them. Now, how is this age? Now the age is simply the same as before, except that, you know, I have a set of vectors containing the different powers. Okay? So this is a vector of 1, this is a vector of t1 with the power 1. I call this one as t2, which has a power 2. Then I call this one as tp minus 1, which is the power p minus 1. Then I do exactly the same. I do exactly as that one. Except, you know, it's a little bit more, it's a little bit longer, but you know, it's the same principle. Okay. And I mean, what I'm saying here is that, you know, if I want to predict, which is x at the time n plus 1, which is I am predicting the future, this depends on a set of parameter theta hat, which is the one that I estimate. If I make a mistake, I make a wrong. If I make a mistake in theta, I make a wrong prediction on x. And so I decide to buy or to buy or to keep the stocks, and perhaps I make a mistake. Okay? I lose money. Now, okay, so this is easy. Clear up to now? Now, I don't look filtering in a conventional way as a convolution. I look filtering as a matrix vector multiplication. One reason for that is the following. Okay, so one reason is the following, you know. The reason to look at the block type representation of the data is that in practice data are always handled in block. So let me give you one remark on that. Now, so why matrices for convolution? Okay, because you know this is the reason of the representation. Usually, if I have a signal, I have a piece of signal. Usually, I have n samples of signal. If you take the homework of last year, I gave you a piece of music. If you look at the homework number 3 last year, you have a piece of data. You need to process that data. So the data are mostly with finite length. So when you say, I mean, in conventional, in a classical signal processing, okay, what you say is that assume that I have an infinite set of samples. But infinite does not exist. So, I mean, my goal is to move from the dream world into the real world. And the dream world is that the ideal filter exists. The dream world is that, you know, the infinite set of samples exist. But this does not exist. So let me give you an example for that. A further example, an additional example. Oh, I keep it that because I will use again. So let's make an example, you know. Suppose that suppose that I have a music, okay, and this music is affected, is superimposed on the sinusoid. Okay? So this is the signal, music, and this is the noise. Actually, this noise is sinusoid. So if you listen to that, okay, so very, very bad. So you start saying, I don't want to listen to that, right? Okay? So when you superimpose, you make this plus that, so you have this, okay? Now, if you make the spectral analysis, we will see what is a spectral analysis, but you know, imagine that I take this one and I put into a magic device which is giving me the power spectral density. So you know, it's 0, my sinusoid is, I don't know, 50 Hertz. Okay? And what I get, I can see is, you know, an annoying noise. Let me see if I can find it. Do you remember this? This one. No. Why? You see? By the way, it's one harmonic to the other. That's another story. Okay? So there is a sinusoid inside in this room. So we are talking and there is a sinusoid. Okay? So if I make that plot rather than making this way, I make it the other way. See, there are lines persisting. Now I don't say anything. Okay? So there are sinusoids, right? Now, so that means that my signal is affected like that. So what I'm describing is not magic, it's something that is in this room. Okay? And most of the case is due to a vent. Ah, no, that. Is due to that, okay, so the projector is the fan, which is the, you know, the cooling vent. Okay, so anyway, it's a light, so we have this noise. Now, you know, so we have my voice, okay, and then, you know, there is this sinusoid. Now, my goal is to remove the sinusoid. Okay? Now, if I want to remove the sinusoid, then you make in digital signal processing, in elementary digital signal processing, you need to make a notch, which is a filter. Okay, so the filter you need to make is this one. It's designed this way. Is unitary, 0, unity. Okay, this filter is called the notch. Notch means because I'm killing one sinusoid. Okay, now. If you expect that this filter is canceling the sinusoid, you get a bad surprise. That filter does not cancel the sinusoid until you are in steady state. This is the concept that I'm demolishing you. The steady state means that you have an infinite set of samples, which means if I start applying the filter from minus infinite, now the filter is, you know, is killing the sinusoid. But if the filter starts now, then, you know, in order to cancel the sinusoid, I need to put another sinusoid, okay, with a negative sign. Okay? So I need to have another sinusoid, which is killing the first, right? So I make this minus that, I get 0. Okay? But when I created the second sinusoid, the transition of the filter at the beginning, the filter makes this way. And then cancel. This is the transition part, the beginning, okay? Because the filter has all the coefficients which are 0, so it's resetted, and the filter starts operating. My goal is to take this block of data, design the filter such that this effect is minimum. In order to design the filter such that this effect is minimum, I need to process the data in block. And this is the reason why when I started talking about the filtering, the linear filtering, I talk about a block type processing. So let's go back to the okay. So why matrix is for convolution? Matrix is because when I take a block, usually what's before, what's after is 0. Okay? But in practice, that block has another piece of signal which I don't see, and another piece of signal that follows that I don't see. So the reason for handling the data in block is that if I process this block of data, this set of data, by considering the processes such that I rule the transition before and after, my filtering is optimal. If I do my estimate or my processing such that, or my estimator such that I take into account the finite length of the data, my processing and my estimator is going to be optimal. So because the processing takes into account of the finite length of the data. So this is, this is the reason. Matrix convolution, it's because I make a processing of block of signals. Okay? They are in block. Sometimes this is called block processing. Or block time process. Okay? So let's see. Beyond all this blah blah, let's see how what do I do. Now, what I mean is the following. If I take the conventional convolution, so xn is equal to gn multiplied by un. Okay? So we have a system. You can imagine we have a system where gn is the impulse response, un is the input, and xn is the output. Okay? So this is the conventional way. Then I can write. You should be familiar with this notation, but so xn is the sum of convolution of gn and un. Okay? So it's the convolution between these two sets of zeros. And let's assume that gn is the impulse response, and the impulse response contains n samples. Okay, just to fix the idea. Now, what I can do is, if I convolve now a block of data, so if un, if my data u is limited in length, so if I have n samples, and I convolve these n samples with a filter response, that, for instance, is n samples. So how long is the input? So the output, you know perfectly, okay? So the output is m plus n minus 1. Okay? This is the support. Support means how long is the response, okay? The output. Now I can write, in a compact way. The compact way I'm writing is the following. So, is that I have a vector u that has a length n, which is convolved by another vector g, which has n length, and the convolution, gets the output x, which is n plus n minus 1. Okay? So this one now, these quantities are the length of each vector. Okay? So x has a length n plus n minus 1, you know, so nothing new, except that I put all the entry into a vector. Okay? So what I say is that this one is a so-called blockwise notation. Why? Because, you know, it's a block of data. Okay? So it's a block of u, that is n, which is filtered by a filter response which has the support n. And what I get is n plus n minus 1. Now, so this one is a notation that we are going to use. Now, can I write in a different way? The answer is yes. I can write in a different way. I can write by using the so-called convolutional matrices. What is a convolutional matrix? Okay, let's see. I write here. Okay, what are the outcomes? So let me get this. I copy. I move it there. I superimpose into the title, which is not important. Okay, so this is the convolution. Now, let's compute the convolution x1. So what is x1? Now, x1, you know, it is g1, g0 multiplied by u1 minus 1. Okay, which is u0. Okay, so x1, it is u1, g1, sorry, g0, x0, I start with 0. x0 is g0 multiplied by u0. What is x2? x1, again, I count by 1, but I should count by 0. What is x1? So x1, you know, is g0 multiplied by u1 plus g1 multiplied by u0. Okay? Then I can do it with x3. Again, you know, it's x2. Okay, so x2 it is g0 multiplied by u2 plus g1 multiplied by u1 plus g2 multiplied by u0, and so forth. Okay. Now, I can take everything and organize into a matrix. So, you know, my matrix has this shape. Okay, so I have a u1, a u0, which multiplies g0. So the first output, so x0, is obtained by the first row times the first column. Okay? So my first row has a lot of 0. Yeah, sure. You know, the only which is saved is the first one. Now, the second is u1g. There is a mistake. Okay. So the second line is u1, u0, and then all the others 0 multiplied by that. So if you try yourself, I get exactly the convolution this way. Okay. So what is the property of these matrices? By the way, you are in x1 and then so forth. Okay. So what is the property of these matrices? Now I change in red because it's the property. This matrix has the property that the block of data is written in the first column. and then all this block is shifted down, okay, one by one.
I guess those should be UN, not n minus 1. Because the k starts from 0.
No, that's right. K starts from 0 and the sample starts from 0. So it is U0, U1, U2, U blah blah, and UN minus 1.
So, for example, we have G0 times UN minus 1 or G0 times UN. If you write xn, try to write xn. We have G0 times UN for the xn.
What? Where is it? Is it here
No,
or there?
for example, you wrote x0, x1 with the blue, you see, on the matrix. Try to write xn. Then you need to write G0 times UN.
No, it's the opposite. Should be the opposite. Okay, so the order is G0, U1, and G1, U0. So that's, the formula has to be modified. Okay. Now, so this is these are the column that I'm describing. Okay. And then I have all the blocks, okay, which are shifted. So this block is the vector of data, okay, which is shifted down. Then I keep shifting until I reach the last position. Okay. Now the size is such that here I have n plus n minus 1. So my matrix is n plus n minus 1 multiplied by n. Now this matrix here, okay, this matrix which has a structure where the first column is shifted down is called the convolution matrix. So the convolution matrix is a matrix where you take the column as it's shifted down, one by one. Now if you look at the same matrix, it has another symmetry property. So in the second row you have a U1 and U0. The third row you have U3, U1, U3, U2, U1, and U0. So, reading into the matrix, you see that the new samples are entering into the convolution, okay, as it should be. So, this one enables me to write the convolution as in the following way. So, I have a vector S that is n plus n minus 1, this vector x, is equal to a matrix U which is accounting for the convolution matrix of the input, multiplied by G. Then now G has the length of the vector is n, which is the impulse response in the system. But since I can, means the convolution commutes, so the property of the convolution is that, I can write as a convolution matrix either U or G. Then I can do a similar example, okay, you prove by yourself. So I can do a similar example where, I can take the impulse response, which is G, and then I can shift down the impulse response, and so I can do the convolution matrix on G, which is similar to the convolution matrix on the input, okay? So again, I can write my data as if x, which is the output, which has a dimension n plus n minus 1, is equal to the convolution matrix G, which is the convolution matrix of the impulse response, time U that has a size n. So right now we enrich our database with new two operations. One is that if I need to write xn equal gn convolved with un, and I have a block of data, I can either write as x equal u, capital U multiplied by g, or I can write in the same way as a g, capital G multiplied by vector u. This is the size is n, this is the size is n, and the size is n plus n minus 1. Okay? Now, in my problem, this u takes the place of age, and this vector takes the role of unknown. So I can apply this method to estimate g or estimate u, assuming that I have u or g. So these are two different problems that I'm going to solve, which have a practical impact. So let's see. Let's look at the identification problem now. What is the identification problem? The identification problem is the problem where, assume that I know u, but I don't know g. So I measure, x, which is affected by noise, okay? And my goal is to get the g. Now, this means that I want to get the impulse response of the system. Now, one example of that. Now, the telecom knows that this is called the channel estimation, but I don't want to make the telecom example. I want to make an example that is common to everyday life. Okay? Now, the example is the following. When you buy a new hi-fi system now, that hi-fi system is digital. Okay? So you buy, the loudspeaker, and you put the loudspeaker into the room. Now, but the new digital system is digital because the system is compensating for the reverberation into the environment. So what are the reverberations? So if you have your room, let me sketch here. If you have your room, and you put your loudspeaker here, okay, in this position, and and you go with a cellular phone. I don't know, have you ever seen the new hi-fi system? They calibrate the system by the cellular phone, okay? So what's happened is the following. The cellular phone is, actually the cellular phone is moving, but let's forget for a minute, okay? So, since I want to listen the music in this position, okay, that's me, that I'm listening to music, okay? So, I want to listen to music in this position, so the music, every time I generate the music is bouncing in the wall. Okay? So these are called reverberation in the room, okay? A kind of echo. If the room is very big, it's like a big church, okay, you have an echo. Right? If you have a cave or you have a tunnel, okay, you have an echo. So depending on the size of the room, you can perceive the echo or not. Okay, if it is very big, you have a big. Okay, so this kind of reverberation. In a small room like this one, okay, there is still a reverberation, but it goes beyond your sensitivity. So now the echo low pass the signal. Okay, so this means that if you want to listen the high frequency signal, you cannot, because there is this reverberation. Okay, so now in order to compensate for that, you need to estimate this G. So this one is acting as a G. Okay, so if you look at this G, you get this G that is tuck, tuck, tuck. These are all the echoes. This is the impulse response. This is time, and this G of t in time. You get this one. Try to see. Okay? Look wherever you want. Then you get this impulse response. So what I can do is that when I play the music, I can play the music, so this is the music signal. I can play with something like G to the minus 1. So if I play with G to the minus 1, I put in cascade G, then I get a clean music. Okay? So this is called the de-reverberation of the environment. This is typical. So you know, if you buy a hi-fi today, it's done in this way. This is the beauty of digital. Okay? So if you want to do in analog signal processing is the electronic. Okay? For me, analog signal processing is any electronic device. An electronic device makes analog signal processing. Okay? And you know, and the our colleague electronics that they want to do everything in analog, they get crazy because you know they need to play with a capacitor, resistor, and then they have a current, and then you know voltage. Oh God, it's saturating, so it's a trouble. Okay, so you see those our poor electronics, which is swearing. Okay, okay. So you know, in order to find the way to make it, and by the way, what it was done years ago was that you have this filtering effect that you calibrate for every room. But you need a genius to calibrate. So there were the genius that could calibrate the room. Now everything is carried out by the phone. How is done? It's done in this way. So you generate, this is a system, okay? So you generate a signal U that is known. So you have a known signal. Now actually this known signal is known to you. Let me put it this way, the calibration procedure, okay? So the calibration means that I put here the U signal, and you know, since I have a cellular phone here, smartphone, okay? So since the smartphone knows you, then you know when I trigger, which means when I transmit that signature U, the smartphone knows that U and processes that U. That means that inside of the smartphone, you create a system that is like this one. So since you know U, but you need to get the G, so you put the U matrix, so you put the generated signal into a vector line, into a matrix line. You create a convolution matrix, then you get this U. So since your goal is to get the G, then you get the G by using that pseudo inverse. So the estimated G is obtained by the pseudo inverse with the measured data of U. And you get it. So you get an impulse response. And so you put that impulse response, you calculate the inverse of that one, and you clean your signal. Okay? Now this is called system identification. So in system identification, you get the data, you know U, so internally you create U, and then you G hat, which is U transpose U minus 1 U transpose X. And in order to make U, you need to take the signature U and create the convolution matrix U. Okay? Now let's.
Professor, in this example, U is the music, the signal, or
Usually, since the people doesn't want to get crazy with the property of U, so you generate U in two possible ways. One way is that you generate U such that you create some harmonics. So this kind of process is carried out frequency by frequency. Or you generate a white noise. If you generate a kind of white noise, then that U is guaranteed that it's full rank and it's easy to be inverted. So there are two major ways to create that. So once you are done with that, U is replaced by the music. Okay? But when you listen to music, you don't want to listen to the calibration procedure. So the calibration procedure is something that you make it at the beginning, before listening to music.
okay. So it's like a generic signal to calibrate?
No,
the
is
system?
is a signal that is designed specifically to calibrate the system. Which means I design you. Okay, I design the signal you. For the telecom people, this is system identification. It's called the channel estimation because in telecom now, you know, I use the green for the telecom one. This is the transmitted data, so the training samples. Why is that? Because, you know, if you take, let's take a very easy way. Let's consider, you know, a block transmission. What is a block transmission? It's a packet, right? So communication now happens in packet. That's another good reason to study block process. Okay? So usually when you are transmitting packets, you have the synchronization part and the payload. Now I'm talking to the telecom, your telecom side. Okay, so you know you have a synchronization and payload. The synchronization is a signal that you know. So this one is you. Then this is received. When you receive, you know you, but you don't know the payload. So what you do, you take with you that you agreed with the base station that you both base station transmits that you, and you are the device that you know what is the base station transmitting. You create the convolution matrix, and you create the estimator of G. That G is the channel response. Once you get the channel, you decode the payload. Okay? So now this identification problem is much more common than you can imagine, right? And you know, for this, for the reason of packet type communication, that's a good reason for processing the data in blocks. Deconvolution. Now I said, you know, remember I said here, first I estimate, then what I do, I clean the signal. Okay? So what I'm talking now is how to make a G to the minus 1. When I say G to the minus 1 means I transmit from the loudspeaker a distorted signal such that this distorted signal is exactly the opposite of the distortion that the environment is creating. So which means I am transmitting from the loudspeaker a signal with the reverberation in the opposite sign. And when you know it's reverberation naturally, then we get a very clean signal. Now, this problem is called deconvolution. Deconvolution means making the opposite of convolute. Now let's see the problem. How is that? The problem is the following. Suppose that you know I have you, okay, and I don't know you. So my parameter to get is this. But this is known. Okay? So this is known. This might be known because I estimated in the previous step. Okay? This might be known for some reason. Huh? So G is known. Then what I measure is X. But X has been distorted by a filter that I know. So my goal is to get U. Now why is it called deconvolution? Deconvolution means make the opposite of convolve, means inverse of convolution. Okay? This is deconvolution. In telecom environment, this is called equalization. Now, you know, signal processing called deconvolution, telecom called equalization. The concept is exactly the same. Okay? So, no, so now let's look how to make it. Now the problem is the same, except that now G is known and U is not known. Look at the question mark. U is not known and G is known. So how can I get U? Well, if I want to get U hat, which is a very clean form of U, then what I need to do, I need to make now the G pseudo inverse of G multiplied by the data X. That's all I need to do. And in this way, you know, I'm happy because on the other side I get a very clean signal. Okay? So, remember, there is always the issue about the noise. Everything related to the noise, I'm not touching. I'm not touching, but we will touch it by next week. Which means, you know, the Friday we will start, you know, to touch a little bit on stochastic processes. Okay. And by the way, the telecom call it equalization because this distortion in the payload is compensated in the equalization part, not still the payload. No. Before that. Let's make 10 minutes break, okay? I continue till 6:30 today because, you know, we missed yesterday.